Welcome to Oddly Real. I'm Nem Stefanovic. The visible ordinary matter that we see in the universe and experience here on Earth can be attributed to just 12 different particles. And of those 12 particles, only 3 are truly part of our everyday lives. The remaining particles are fairly rare and really only found in exotic materials or unusual situations. Additionally, there are only 4 forces that are responsible for all of the interactions of matter in the universe. And of those 4, really only 2 are experienced by us as human beings. Let's appreciate how extraordinary it is that the building blocks of all of nature can be summarized with just a few items in a short list that can be printed on a t-shirt. In this episode, we'll learn a little bit more about those few particles and forces that make up almost our entire reality. There are only 12 fundamental particles that comprise the visible universe. We can break down these particles into 2 main groups, quarks and leptons. The 6 quarks, in order of increasing mass, have rather interesting names, such as up, down, strange, charm, bottom, and top. The leptons are listed as the electron neutrino, muon neutrino, and the tau and tau neutrino. All of these particles are considered to be fundamental, meaning that they are whole, not made of any other particles, and there are no internal parts or components within them. So how does this relate back to common matter in our world? All matter is made of atoms. Originally, atoms were thought to be the smallest indivisible unit of matter, but it was discovered that they are not fundamental at all. They have an internal structure made of a core nucleus consisting of protons and neutrons, as well as surrounding orbitals of electrons. The electron is a fundamental particle. However, notice that protons and neutrons are not part of our list of fundamental particles. This is because it was also discovered that protons and neutrons are themselves not fundamental, but in fact have internal structures. Those structures consist of quarks. The proton is made of 2 up quarks and 1 down quark. The neutron is made of 1 up quark and 2 down quarks. It is the quarks that are fundamental. Historically, it was also assumed that electrons and protons carried fundamental charges of -1 and +1 respectively. Here, we mean that the charges are actually multiples of the basic charge unit of the proton, which is 1.6 times 10 to the minus 19 coulombs. It is easy to find out that actually quarks have fundamental charges of the up quark being 2/3 of a charge and the down quark being -1/3 of a charge. We also have the additional fundamental charges of -1 from the electron particle, which itself is fundamental. This makes 3 basic charges in total: 2/3, -1/3, and -1. Interestingly, this means that neutrons carry charge within them. However, the charges of the quarks in the neutron particle, when summed, result in a total charge of 0. Yet, when you probe deeply into the neutron, the charges reveal themselves. The quarks can be grouped into generations. Notice we can group the quarks according to the 2 possible charges that they possess: 2/3 for up, charm, and top, and -1/3 for down, strange, and bottom. The masses of the quarks increase as you move up the generations. The most common quarks in the universe are the up and down quarks. The quarks in generations 2 and 3 are much rarer. These quarks were discovered using particle colliders at very high energies and very high speeds, enough to produce the heavier quarks. The situation was much different in earlier times in the universe when matter was much more energetic. Scientists believe that the heavy quarks played a much more important role in the reactions that were taking place. This is part of the reason why learning more about quarks helps researchers to understand more about the early universe. The leptons are also arranged across generations. lepton mass increases as you go higher up the generations. The electron has heavier counterparts called muon and tau. For example, the muon is 200 times heavier than the electron, and the tau is 17 times more massive than the muon. These particles all possess the same charge and respond to the fundamental forces in the same way. One major difference, other than the larger masses, is that the muon and tau both decay into other particles, but the electron is stable. Muons have a lifetime, or average life, of about 2/millionths of a second, when they decay into an electron and neutrino particles. But recall that we said that the muons were fundamental particles without any internal components. How can they decay? Interestingly, the answer comes from Einstein's theory of relativity. There's nothing inside the muon that comes out of it. Instead, at the moment of decay, the muon disappears and is replaced by an electron and the neutrinos. It happens because energy is transformed from one type to another. This is a consequence of E equals mc squared, which basically means that matter and energy are equivalent. The energy in the muon is converted into an electron and two neutrinos. There's some mystery to the heavier leptons, since there isn't a good reason why they should even exist. Unlike quarks, which are both predicted by theory and have a firmer basis for the roles they play, this is not the case for leptons. There's a certain beauty to having the number of quarks match the number of leptons, but more research is needed to understand why that's the case. Muons are observable in certain experiments from cosmic rays, but the members of the third generation have not been observed in naturally occurring processes. However, it's thought that these would have been produced frequently in particle reactions in the early times of the universe. The other three leptons are neutrinos. As their name suggests, they are electrically neutral. This is different from the way neutrons have zero charge, since neutrons are composed of charged particles inside. Neutrinos have no components in them, so they genuinely carry no charge. In fact, neutrinos carry a very tiny amount of mass, less than 1/10,000th of an electron, which is also considered a particle of small mass. These properties mean that they interact very weakly with other matter, which leads them to be labeled as ghost-like particles. Neutrinos are generated in enormous amounts in nuclear reactions within the sun. Around 10 to the power of 12 electron neutrinos pass through your body every second. However, neutrinos react so rarely with matter that this poses no concern for our health. There are four fundamental forces in our universe: gravity, electromagnetic, strong, and weak forces. Of these, really only two, gravity and the electromagnetic force, are what we experience directly as human beings. I don't need to spend too much time describing the force of gravity, since we feel the effects of gravity pulling us down, and we see its effects in lunar and planetary orbits. Similarly, the EM force, or the electromagnetic force, is responsible for everything from being able to see using visible light to the physical properties and chemical reactions of matter. People are typically far less familiar with the effects of the strong and weak forces. These only act over extremely small distances. For example, the strong force acts in a range smaller than 10 to the power of minus 15 meters, which is the size of an atomic nucleus. The weak force has a range of 10 to the minus 17 meters, which is even less. A proton on one side of a nucleus would be too far away from a proton on the other side of the nucleus to experience any weak force interactions between them. The strong force only acts between quarks to hold quarks together. It acts to create a stable atomic nucleus. Otherwise, the repulsive forces of the protons there would blow it apart. The leptons are not affected by the strong force at all. This is the same idea that a neutral particle will not be affected by the electromagnetic force, since it has no charge. However, both quarks and leptons feel the other three forces. Note that leptons do not bind together to form other particles, and that's a major difference between quarks and leptons. We cannot isolate single quarks without other quarks. They are always bound together. Any newly created quarks, such as those created in a particle accelerator, will combine with another more quickly than can ever be observed. The weak force is the most unusual of the forces, since it's not characterized by an attraction or repulsion effect. Instead, it changes particles from one type to another, and it is responsible for certain kinds of radioactive decay. The weak force is what gives the generational structure of quarks and leptons. The weak force is felt by both quarks and leptons. If two leptons come close enough to experience the weak force, there's a possibility that they can be changed into other leptons. It is only possible to change leptons within the same generation into each other. Electron to electron neutrino and vice versa, but not into muon or muon neutrino. The weak force acts within lepton generations, not between them. There's actually a law of lepton conservation, which is one of the fundamental rules of particle physics. It states that in any reaction, the total number of particles from each lepton generation must be the same before and after the reaction. Quarks are also subject to the weak force, so they can change from one quark to another. This occurs typically within generations like in leptons. However, unlike leptons, quarks can transition across generations, although not as easily. We'll end with one more fact about neutrinos. Interestingly, neutrinos primarily interact with the weak force. They don't interact with the strong force and have no charge, so they also don't interact with the electromagnetic force either. Even their interaction with gravity is small, since they have such little mass. In order to shield against a significant number of electron neutrinos, you'd need a block of lead that's 90,000 million meters thick. We are able to detect neutrinos here on Earth as they pass through the planet. The largest detector is found in Antarctica, called IceCube. It's in the South Pole Neutrino Observatory near the Amundsen Scott South Pole Station. It's buried under the surface at depths of 2,500 meters. It has 5,160 digital optical modules attached to vertical strings that are positioned across a 1 cubic kilometer. We can't observe neutrinos directly. However, when neutrinos interact with the ice, new particles are created. For example, a muon can be created that travels through the detector in a path. Those readings can be analyzed to understand about the neutrino that created it. Thank you for watching this episode, and remember, oddly real, really interesting.